Okay, this particular substitution is really a special case of a differential equation. We have a differential equation, and then we happen to see some ax plus by plus c, or some combination where, I guess y cannot be equals. I guess I don't know. One of those has to be non-zero. Um, Otherwise, if a and b are zero, then it's it's just a constant. Um, but if a or b is equal to zero, then it's separable. And so what we're looking at here is a sort of a form, and it's really special case form. So um, not likely to run into this, but every once in a while we do. And so we'll make the substitution for u and change the variable into u as a function of x. So we're going to do the regular derivative here. Um, and this should come out to be straightforward. So let's see if we can find a problem to do. Um, Sorry, I'm going to block that for a minute. And just to get a feel for how this thing might look like. Let's take a look at a couple of problems. So not that we need to identify f, but you can see what f should equal to in these cases. F of whatever is just going to be the squaring function, and the thing that's inside of the squaring function is ax plus by plus c, where a, b, and c are all equal to 1. So this falls in that category. This, by the way, is, well, it's not separable, and if you FOIL it out, it's not a linear differential equation. It's not Bernoulli, and it's not any of those types of differential equations. So we're going to see if we can take advantage of using this special substitution to help us solve for number 23. I usually do even problems. Let's do number 23. So we're going to let u equal to x plus y plus 1, and then your differential equation will be u squared. Actually, it's not just going to be that, so we have to be careful and also replace our dy dx. So what we're going to do is we're going to take the derivative of both sides with respect to x. Let's say d dx. And so this is going to give us a du dx. And dx is 1, dy dx plus dy dx, and plus 0, because that's just a constant. And so now here's our substitution for the derivative. So dy dx is equal to du dx minus 1, and that's what we're going to substitute in for dy dx. So what do we have after all that? We have du dx minus 1 is equal to u squared. Is this easy? Suppose we can separate it. It looks like it might be separable. So du dx equals u squared minus 1. Now u squared minus 1 has to be together. You get plus 1. Thank you. Du over u squared plus 1 is equal to dx. Now we've separated it. Now we're going to integrate. You guys know the integral of the left-hand side? Don't say ln. Don't say ln. No. What? It's the arctan. We knew that, right? Okay, it's the arctan. Arctan of u on the left-hand side, and then the antiderivative of 1, there's a 1 dx there, is x. I'm throwing a plus c, so u is equal to the tangent x plus c. And remember, like our u substitutions back in Calc 1, we have to, change everything back in terms of y. What was y equal to? U equal to? Oh, u equals x plus y plus 1. So x plus y plus 1 is equal to the tangent. And then y is equal to tangent x plus c minus x minus 1. By clean, you mean you can read my writing? No. Oh, no. Can't read my writing and it still makes sense. Yes. Must be a good thing. So this is a little bit more straightforward than the other substitutions that we had to make. We didn't have to invoke the chain rule, product rule, or anything weird like that. This is a straight substitution. It's a linear substitution too. The u and then the x and the y are not being raised to any weird powers. I mean, they are when you put it in to change your differential equation, but that's okay because that's not a big deal. But this substitution itself, if you focus on that and what happens to the u when it becomes a du dx is about as simple as it gets. So this is our simplest substitution that we have. So let's see if we could do this one real quick. So they say b is not equal to 0. I think maybe if a was equal to 0, then it's also not needed. I mean, you don't need to do this substitution. So, but c can equal to 0. In this case, c is equal to 0. So our du dx is 1 plus dy dx. And that says that dy dx equals du dx minus 1. And so we change everything. And I guess we're going to, oh, I don't know if this is easy anymore. Oh, nice, the first one. All right, we're going to probably separate it again. Du dx equals tan squared u plus 1. And then we'll separate it. Oh, we know what tan u is. Tan u squared, tan squared u plus 1. Isn't that like an identity? Secant squared? All right. Secant squared u. This is pretty much done, right? Let's move on. Let's finish it. Du over secant squared u. Oh, what's secant? Cosine? Sine? Cosine. Definitely sine. I think it's cosine. Cosine squared u du dx. Oh, I hate this. I mean, this is requires some sort of formula. Yeah, I just want the answer. What is it? Something like that. Yeah. Not on the test. One half. Ah, looks good. You know your half angle formulas? There he goes. All right. Let's finish this up. Solving for this doesn't look like it's going to be very easy, so this might be a case where we might have to leave it in, what's that form called if you can't solve for y? Implicit. So I think it's x plus y, right? That's our u substitution. Our u substitution was x plus y. So 1/2 x plus y plus 1/4 sine of 2x plus y is equal to x plus c. And kind of difficult to solve for y, so we'll just leave it at that. Yeah. Do what on the test? Well, I think if you can solve for it, then you should solve for it. You don't like that answer. Yeah. 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 Michael, say it again. I don't know. That's the hard part. Holy cow! I can't solve for this. Y plus 2 is equal to x plus c. Oh, I can't solve for that. That's too hard. I mean, it is a judgment call, so I don't know. Michael, I'll try. I'll try to. The thing that I just erased. I, so yeah, I don't know if I'm going to be able to tell you if you can leave it as an implicit or explicit solution, but I'll try. All right. So there's a handful of integrals that you're going to need to know. I don't expect you to memorize integrals, but you should know how to do a bunch of integrals from Calc 2. On exam situations, you are allowed a sheet of notes, 8.5 by 11. So fill that up with integrals. Front and back, yeah. Okay. You can write techniques, examples of things that we've done in class or homework or whatever. You can write a poem. You can put a picture of some flowers. I don't know. Yeah. Then you could type it and shrink it, except you can't bring magnifying glasses to the test. That means you shrunk it too much that you can't read it, so that's not cool. Then you're gonna bump into walls when you're walking. Yeah. I think it's everything that we've discussed had in the homework. And sometimes I also might not talk about it in class, but I say that there's a video of this online that I made. So anything that I made in terms of videos in class or outside of class is all fair game. For example, did we skip a section here and then made a video of it, or 1.3? So for example, 1.3, we didn't do that in class, but there is a video of it, and I said that you're responsible for doing that. And if you did follow that video, you would have been able to do the homework, right? Especially that last one. That was so hard. Okay. Any questions? I mean, you probably have lots of questions, but let's move on. So, as per usual, the difficult part in now doing these differential equations is that when we're doing it section by section, it's clear which technique we're looking at and which technique we're practicing. So in a test situation, I'll say do this differential equation, but I'm not going to tell you what technique to use. So you have to look at it and determine what to use and how to approach it. So the place to go for problems like that would probably be the review sections. And here's a portion of the review section in chapter 2. So let's copy this whole thing, put it in our notes, and then do a couple of these problems. Ooh, that's going to be in the way. So these are all first order differential equations. At least it gets narrowed down that way. And let's practice looking at it and then decide what kind of differential equation it is, and then pick a couple of them to do. Okay, so some of these you might need to rewrite so that you can try to make sense out of it. Let's start with A. If you're looking at that, and then I said, this is a differential equation, you should try to solve for it. How would you approach this differential equation? What kind of differential equation do you think this is? Let's go through the list, right? Well, let's make a list. What are the differential equations that we've learned how to solve for? Separable. So how do you spell separable? Okay. So first order linear is the one that has an integrating factor. What else? The one with the partials. What are they called? Exact? Something like that? Is that right? Exact. DE. Bernoulli. Homogeneous. Let's do homogeneous functions. Then Bernoulli. And then the other substitution. Let's call it a linear substitution. That's what we were doing today. So these are the techniques that we've learned so far. And for the homogeneous and the Bernoulli, you need to know what they mean to be homogeneous and exact. You need to know what they mean to be any of those types of differential equations. And then the other thing to do is that when you first look at a differential equation, it might not look like any of these from the beginning, which means you might need to, work it out, change it around, give it a different look. And after you do that, then you might get the form that you're actually looking for. And actually, after you change the look of a differential equation, it might fall into more than one of these categories. So you may have an opportunity to solve for it in a couple of different ways. So back to the first one. Let's go through it. Is it separable? Do you think you can separate it? Say it again. Yeah, so can we manipulate it to make it separable? What kinds of things can we do? Oh, we can cross multiply, right? Separable just means you get everything, get all the x's and y's to one side. If we cross multiply, do we get something that's separable? We have dy times x, and then dx times, dx times x minus y. You have this x minus y here that's going to be hard to take apart. It's going to be hard to take them away from each other, so I don't think it's separable. Yeah. So we could possibly get first order linear if we split them up. So let's see. Should we go through the work to show that it's not separable? Why not? Sure. So for A, we got x times dy is equal to x minus y times dx. And then at this point, this is where you're going to have to stop and say it's not separable. You can't separate this. You can't divide by a y to get rid of things. So let's say not separable. So let's try something else. Um, so Michael suggested that we split this up. dy dx is equal to 1 minus 1 over x, or y over x, right? And then we can rewrite this as dy dx minus or plus 1 over x times y is equal to 1. So now it looks like it's a first order linear. So first order. And then from here we can do the integrating factor to solve for this, okay? So not interested in solving it right now. Let's move on to another problem and see if we can determine what kind of differential equation it is. So let's take a look at B. So whenever we see the x and y business that's being added or subtracted, it kind of takes us away from the separable because it makes it hard to separate. So I'll just go off and say, no, it's not separable. So anything you can think about doing for B to try to make it look like, what's that called? First order linear? We can divide by dy dx, or we could switch the numerator denominators. But then you have a dx dy, which kind of takes us out of the running for being able to solve for that. I don't think that'll work. What? I don't know. What? We could. So what we're saying here is possibly say dx or dy is equal to y minus x, and then solve for this like x is a function of y. And then eventually you'll have to solve for y because y is the original variable. So you could do it that way, I guess. So now we can make it look like first order linear. Can we use something else? This looks like a linear substitution, possibly. Let's see. if we let u equal to y minus x plus 0, and then du dx is going to be dy dx minus 1, and then we would have du dx plus 1 is equal to 1 over u. Now, this might be more difficult, but how would you solve for this? Is this a first order linear? I think it could be separable. I don't know about first order linear because the u is in the denominator. Then we're doing so. Yeah. So this could be a couple of things. First order. This could be separable, and also first order linear. X is a function of u. And then remember that you have to change it back into y as a function of x as your eventual solution. So that could be done in a couple of different ways. Okay? How about the next one, C? C looks like it could be C looks like it's separable. You can separate it. It'll be dy over negative y plus 10 is equal to dx over x plus 1. So it looks like it'd be separable. Can it be something else too? It might be. So if we could split this up, put the dx on the other side, we have x plus 1 dy and minus y plus 10 dx. X plus 1 dy equals minus 10, what? Minus y? And so we generally want to bring everything to one side to set it equal to 0. We got negative minus y. Can I just put y minus 10? Dx plus x plus y dy is equal to x plus 1. Is this, what's that called? Exact? We take the derivative of x with respect to y, and we take the derivative of the m with respect to y, and we take the derivative of n with respect to x. We both get 1. So this is exact. And it's probably homogeneous too, right? You replace the x and y with a tx and ty. So, so there's a few ways to solve that one. Let's see. Let's skip D. Let's pick a couple more. I was thinking about doing all of them, but that's going to take too much work. Pick a couple more. Which one do we want to see? What? H? So let's take a look at H. So this is a little tricky. We got that business over there, the x dy dx is equal to y e to the x over y minus x. What's that called? Homogeneous. Yeah. Does this bring back memories? So remember we had some expression like this, and then we checked if it was homogeneous, and it worked out nicely. So this might work out nicely too. So well, first we need to break it up. And I think we're going to need to break it up like this. So x dy is equal to this whole thing times dx. And then we can bring it all to one side, or we can work with this because we just need to figure out the if it's homogeneous. So we're going to check if it's homogeneous. We're going to take our function m. We're going to put tx and ty. There's only an x in there, so that's just t times x. T. Okay, that was silly. Our next one is n. This one's a little bit more complicated. So ty e to the tx over ty minus tx. So the powers of the exponential function can cancel out, and then we can factor out a t from the two terms. And then we're going to get t parentheses y e to the x over y minus x after it's canceled out. So this is your n. So we see that this is homogeneous. And if it's homogeneous, then we can use that technique, whatever that was. We're going to let u equal to, or y or something. Y equals u x, or v equals, I don't know. You guys can look it up. All right. Any questions? This is your task. Your task is to look at a differential equation, identify it. If it's a first order differential equation, it would fall into one of these categories. And if it falls into one of these categories, you should be able to solve for it. Okay? Yeah. This is an exhaustive list of everything we've covered. I don't know if there's any other ones that exist out there. There might be. Yeah. Oh, I don't know. Do you guys have a schedule in the thing? Did I post that? No? Yeah. There's some nods, some shakes. Suppose I can find out. Schedule. Tentative, of course. February 20th. Right? It's not here yet, so. What? Oh, that was modeling here. We skipped it, but it was like I said, it was videoed, and so you guys were looking at it, and you guys had homework for it. So I think it's free game. Okay. What's a Bernoulli? Oh, Bernoulli has some special form. It almost looks linear. Yeah, so it almost looks linear, except for that last bit. So this is what makes it not linear. This term over here makes it not linear, but there's some differential equations that have a form like this, and so this would be a Bernoulli, and this is this. There's some sort of substitution that you need to make. All right, let's see. Maybe we have a little bit of time to do a first order with a, what do you call it? IVP? Yeah, yeah. This one? Yeah, that's probably a Bernoulli. Oh, that's also separable. Yeah, correct. Bernoullis are nonlinear. Should we try to do number 34? Yeah, let's do number 34, and then we'll move on. So I just want to keep reminding you that a lot of stuff that we're doing are looking for general solutions, but every once in a while you're going to come up with an IVP, and you have to solve for that constant that pops up out of nowhere. And also the different variables that they use, like this one has a y and a t, so you have to know the independent dependent variable, just like the r and theta, one of the problems that we did. Okay, let's see if we could do this one. What kind of differential equation is this? Could this be Bernoulli? Let's see. Dy dt equals, should I multiply it out? Now it's separable. Okay, so dy dt equals negative 2 t plus 1 d or y squared. So separable. And then we'll solve for this. dy over y squared equals negative 2t minus 2 dt, just for the sake of integrating. The integral is negative 1 over y, right? Not the ln. And then negative t squared minus 2t plus constant. So here's a good time to pause and think about what we need to do. If we were solving for this as a general solution, then we would solve for y and be done with it. But we have an initial value. So we have two choices. We can continue to solve for y and then solve for c, or we can solve for c at this point, because at this point it looks like it's fairly easy to solve for c. And then continue to solve for y after you know what c is equal to. So there's a couple ways of doing it, and let me solve for c first. And particular example. And what you could do is either later on or some other time, you can try to solve for y, and then after you solve for y, then put in the values for y and t to solve for c. So let's solve for c. We have t is equal to 0 and y is equal to negative 1/8. So on the left-hand side, we get negative 1 over negative 1/8. That's going to be an 8, I think. 0 squared, 2 times 0 plus c. So once we have our value for c, we can just plug it in back to the equation that we found, the general solution. And then we can solve for y. So what is this? You throw the negative sign on the other side, and then you take the reciprocal. So y is equal to 1 over t squared plus 2t minus 8. Now we have the particular solution for this IVP. Okay? That was easy. We should have. Another one with a different technique might have been a little bit more interesting, like a Bernoulli or homogeneous or something. So do those problems in your homework and then see what you're comfortable with, see what you're not, and then continue working on it. And then, yeah, you guys will be ready for the quiz on Tuesday. Sure. Right? I don't know. During a week where we have an exam, we probably won't have a quiz. All right, let's move on. Let's leave all this behind us. Not too far behind. So in calculus, after you learned all these integrals, then they stop and say, hey, let's go back and take a look at those integrals again and find approximations for them. So these approximations are really useful if you can't solve for these differential equations for some reason. If for some reason you're just working with a pencil and paper and you don't have any calculators or anything weird like that to work with. But we have computers to figure a lot of these things out. And so we're going to try to figure out how to do this using some numerical methods, how to solve for some initial value problem. And this is one numerical method that may not be so efficient, or how do we say, good. But we're hoping that it would be a good beginning to understand that sometimes when you're doing linear or doing differential equations, you may not want the whole solution, that function is a solution, but you may want to figure out what that function is equal to at a particular point. Is this 2.6 or 5 or something? 6? So in this particular scenario, what we're doing is we're taking advantage of this as being a first order differential equation. And first order differential equation means that there's a dy dx there. Dy dx for us is a slope. And so we're going to go back to the idea of a slope field and figure out how something works. So if we do a simple example that we already know the answer to, for example, let's say dy dx is equal to y. So quick, what's the answer? Y equals e to the x times a. What? Plus c times a? Same thing. So let's throw in an initial condition. Y of 0 is equal to 1. And then we want to know, usually something close to 0. I mean, 2 is not really that close, but a problem like this would limit you to just be able to approximate what the solution is of that function evaluated at some point that's close to the initial value. So 2 is fairly close to 0. And in a particular scenario like this, you'd be interested to know what y of 2 is equal to. Now, you don't care what y is. In this case, we know what y is, but let's pretend we don't. You don't care what y is. You just want to figure out approximately what this is going to equal to. So what are we going to do? What they tell you to do in that little spiel up there is to use linearization and take steps. And we could do this with slope fields. I think slope fields kind of complicate things a little bit, but try to imagine a slope field in the background. We're going to do it without a slope field. And what we're going to do is when y of 0 is equal to 1, we're actually at this point 0, comma 1. And then what we're going to do is we're going to figure out what the next step is from here. We want to figure out what happens at 2. And what we could do is we can take steps. So how many steps you take, the more steps you take, the more calculations you have to do. But the less steps you take, the less accurate you're going to be. So there's a way, there's a balance, a balance of you want to be accurate or do you want to do a lot of calculations? So that's the scenario that we're looking at. So let's, just to make it simple for now, let's take 2 steps. In this case, we're going from 1 to 2. 2 steps would mean we're going to take big steps of 1. And then from 1, we're going to take another step to 2. And we're going to use this idea of linearization. So what does linearization mean? I have a point that I'm starting off with, and I have a slope at that point, right? So from step 1, I have the slope m is equal to dy dx. And then this is a dy dx when x is equal to 0 and y is equal to 1. That's the point that we're at right now, right? So here I only have a y, so my function, my slope does not depend on x. But y is equal to 1, so my slope must equal to 1. So that means from here, I'm going to have a slope of 1, right? So from there, I'm going to have a slope of 1. And what I'm interested in is I want to know where this is going to get me up to my next point. Does that make sense? Up to my next point. Yeah. Because dy dx is a slope, and then I said x is equal to 0 and y is equal to 1 here on this function. And so I put 0 in for x, there's no x's. I put 1 in for y, there it goes, it's 1. Should I put y? This is a slope. And that's equal to 1. So the slope is the dy dx. The slope is the derivative. So what do I need to do to find this point? This point, well, I know the point has a 1 for x, right? Because it's on 1. How do I find the y value? So this is a line, right? We need to make a line out of it. So y minus y1 is equal to the slope x minus x1. So I guess I use zeros there. Zeros. So this is your slope is equal to 1. And then I have x minus x naught and then y. I mean, y naught. Guess I should write it backwards if I'm trying to follow this. Y naught would be first, and then slope, and then x minus x1, x naught. Is that okay? So I got 1, x is equal to 1. That's where my point is, right? I'm looking for the y value. And then x naught is the starting point. X naught is 0. And y naught is 1. So this must be 2, right? So now we're going to do the same thing, except by the time you get to 1 comma 2, your slope would have changed, right? So imagine again the slope field's in the background, your slope probably changed over there. So we have to figure out what your slope is at this point 1 comma 2. So second step for our 2-step process. We got the slope now is dy dx evaluated at the new point that you're sitting in. You're sitting at the point x is equal to 1 and y is equal to 2. Again, x is not part of the equation, so we're going to just ignore that. And y is equal to 2. So your slope is going to be equal to 2. That means from this point, you're going to be a little bit steeper. And now you want to know what happens by the time you get to 2. X is equal to 2. This has a slope of 1 and a slope of 2, this line. So we want to figure out what our y is equal to. Oops, this is a 2. We want to know what y is equal to. And so we put it back into that thing again. And y minus y1 is equal to the slope. Let's put parentheses. x minus x1. And so the slope in this case is equal to 2. I should have been using different colors here. Sorry. And then the last x where you left off at was x is equal to 1 and y is equal to 2. So y is equal to 2. Oh, this is a plus, minus, plus. Plus 2 times, and then the x that we're looking for is x is equal to 2, and then the x where we were at before is 1. Is x minus x1 confusing? Because you know what that is? X minus x1. X minus x1 is just h. This is h. Anyways, what do we get here? 4. 2 plus 2 is 4. Okay. So that's fairly boring. So with our two-step approximation, we get a y value of 4. Taking 2 steps, get y of 2 is equal to 4. Okay, do we know what y of 2 is for reals? I think we did this in our head, right? We know in this particular scenario, we're not always going to know, but in this particular scenario, we know that the solution is e to the x. And so we're looking for y of 2. So what's e squared equal to? I hope it's close to 4. 7? I don't know. Whoa, we missed by a lot. So this is, we're way off. Yeah. So maybe we need smaller steps. 2 steps, fine. Kind of. So if we break it up to small pieces, does that sound familiar? Like your integrals? If we have a smaller subinterval, then we get a better approximation for the area under the curve. So that's the same thing. Well, I'm not going to do this by hand. But you could do this with a simple program like Excel. You can use Wolfram Alpha to get the answer. No approximations needed. So how are we going to do this? We're going to start off with x and y. And then we're going to start off with the initial condition. So this is the 0th step, first step, second step. And then we'll take, we'll do exactly what we did here with h. With big steps where h is equal to 1. And let's figure out what we need to calculate for our steps. To get our calculation here, our h is equal to 1. To figure out our calculations, we need to add 1 to this thing, right? Plus 1. It's equal to the previous one plus 1. Copy. So the calculations that we had to do was the calculation where we had to find the equation of the line. We had to take the previous y value. So this is going to be equal to the previous y value plus the slope. So we need to define a function. Boy, I'm not doing this correctly. I don't even know why I'm doing this. Why am I doing this? Oh, your slope is just y, right? Your slope, in this particular example, your slope is y. All right, so this is equal to y1 plus the slope. The slope is just y. Times the previous x value, the current x value, minus the previous x value, which is always going to be h. And then if we copy that down, then we're going to get 4 that we found earlier. Yeah, because this is linearization applied to differential equations. This is a differential equations class. Now let's make smaller steps. So we have our steps 0. Let's make our steps to be 1/2. And so our x is going to go from 0, and then we're going to add 0.5 to that. This plus 0.5. And then we're going to keep doing that until we get to 4 to 2. Two. And then we're starting off with 1. So the idea is that we're going to, let me start this over again. We're going to, the formula is that this is going to be the previous y value plus the slope, which in this case the slope is the y value, times x minus the previous x. And then so if we copy that all the way down, we got a little bit better. It's still not very good. So let's see if we can do this with smaller steps. Let's put 2.5. One more. So this is going to be 1, right? And then our formula again is the y plus the slope, which happens to be the y, and then x minus, it's not So we're inching closer and closer to, what is it, 7.38. So that's a little promising. And the smaller steps you take, the closer you're going to get there. Oh, by the way, another thing that I was interested in doing is not draw, insert.
Is there someone who the limit is the number of steps a person can read?
We're not going to do limits for this. We're just going to get smaller and then stop at some small value. Yeah. Well, no. No, because it's the number of steps that you're doing, and each of these is an actual step, and it's not like the size of something. So, all right. Yeah, I think the homework. Oh wait, I still got like 3 minutes left. Sit your ass down. That was recorded, huh? I'm going to ask you to download a mathematical, like for those people who are in my linear algebra class, you've already done this. But if you're not, then I'm going to ask you to download a mathematical like program. And there's two programs that are mathematical like that are free. One of them is called FreeMat. The other one is called Octave. And what I'm going to do is I'm going to ask you to type up commands to solve for some of these differential equations using this numeric system. Okay? MATLAB. Yeah. Yeah, it's its own language. So what I'm going to ask you to do is it'll be a worksheet, a quote worksheet that's probably going to be due Tuesday evening. So if you're planning to do work for this class over the weekend, then the weekend might be a good time to do it. I'll post it up today or tomorrow. Yeah. It would be the same for those three languages because they're the same thing. All right. Yes.